Hello, and welcome to episode number 16 of CS350 Online. I'm your host, as always, Leslie Eisted, and in today's episode, another completely new topic. Isn't that exciting? So there's a few things that I wanted to mention to you just so that you are aware, because I only just became aware of them myself. One of those things is that March 15th and 16th are an additional break. So on the 15th and 16th, there will be no class. So next Tuesday, there's not going to be a live stream. So I just want to make sure you're aware of that, just in case you're tuned in at early 9:30 in the morning. And I know that's really early for most of you. But I don't want you to wake up unnecessarily early and find there's no stream. There's no stream on Tuesday of next week. So our next episode will actually be 1 week from today. So that will be next Thursday. So that's kind of exciting, right? You get a little mini break there. I think that's kind of nice. It's always nice to have a break. And actually, the reason why they're doing this has to do with the virus, I guess. I don't know. Anyways, who's going to complain? It's a break. Everybody likes breaks, and I think breaks are good, especially because I'm sure you are very busy with assignments, not just from this course, but from other courses as well. So that'd be nice. The other thing then is, when are we going to talk about assignment 3? So as most of you know, assignment 2 I think is actually due tomorrow. If you are still working on it, this is where it's really go time. Don't forget, however, there are slip days. You can use up to 3 slip days. There's nothing special that you have to do to use a slip day. All you need to do is just submit it after the deadline, and we will take care of the rest for you. So you can use up to 3 on this assignment. Remember that you only get 5 for the term, and you don't want to overdraw them. And if you need any assistance, of course, there's Piazza. You can email us, and our lovely IAs and Humor are also running office hours as well. And I think I've gotten around to everybody who's emailed me, but if I haven't, I will get to you as soon as possible, because obviously we want to make sure that all your problems are solved before tomorrow. Which means that next Thursday, since the assignment 2 is due on Friday, it means that Thursday we'll be doing assignment 3. We'll be talking about how to do assignment 3 in class. And assignment 3 is the last assignment this term. And it's going to be fixing the virtual memory system for OS 161. We actually don't have any assignments for scheduling devices or file systems, which is kind of weird, I know, because, I mean, when I took this course, we had a file systems assignment, but we don't have that anymore. Maybe in future terms, who knows? We are trying to change up the assignments a bit, so maybe we'll have that in the future. But for now, assignment 3 is the last one, and it's on virtual memory, and we'll talk about it a week from today. And if you want to get started, of course, you can look at previous terms discussions of A3. It's pretty much the same, but I like to have the live experience. All right, so then, those are all the announcements we really have today, so let's look at the OS of the day. So today's OS is actually kind of exciting. It's called Qnx, and I'm going to assume that a fair number of you have actually heard of this operating system, but what's kind of fun about it is it actually has ties to Waterloo. So this was created in 1982, and it was created by Quantum Software Systems, or that was the original company, but it is now actually owned by BlackBerry, and it's so weird to call it BlackBerry because when I was an undergrad, it was called RIM, and people applied for RIM jobs, not BlackBerry jobs, and of course, the university was surrounded by RIM, and now it's like non-existent, but anyways, BlackBerry/RIM now owns QNX. Now, how did this operating system get started? So, once upon a time, 2 gentlemen, Gordon Bell and Dan Dodge, took a course called Trains. I'm sorry, I don't know the course number. It's the real-time operating systems course in 4th year, where you try not to crash the trains. And they thought to themselves, it would be really cool if the world had a real-time operating system. And so because they weren't busy enough taking trains, they decided to actually create their own operating system, like a commercial operating system, that was real time. And so they did. And it is a Unix-like operating system, and I have actually used this OS before. I think I've said it before, most kids when they go to college, they're trying, all kinds of things. Oh, let's have parties and things like that. I was more of that, let's try different OSs and different programming languages. And QNX is one of the ones on the list. So it's very Unix-like, but it's real time as opposed to something like GNU Linux or Mac OS or Windows. And you might be like, but aren't those real-time operating systems as well? I mean, it appears that they're doing things in real time. I mean, Yes and no. So the difference between something like Windows and QNX is Windows will respond to events, and it tries to be very responsive to threads that are interactive, which we now know how that works because of the multi-level feedback queue discussion we had in the last episode. But it doesn't really make any guarantees as to between you pushing a button and the thread getting the notification that that button was pushed and being able to respond to the push. There's no guarantee on how long that's actually going to take. Whereas with a real-time operating system, they actually have to put in guarantees. The camera sees a person crossing the street. It responds in X microseconds to stop the vehicle so that you don't hit the person. So real-time operating systems have these built-in guarantees because they want to make sure that when an event happens, it is handled as quickly as possible. Hence why they are designated as real-time, because they're making those guarantees. Now, the other interesting thing about QNX is unlike Windows or Linux or anything like a Mac OS or iOS or Android, it's a microkernel operating system, which means that the kernel actually contains the bare minimum of things in it. And in fact, their kernel was originally only 44 kilobytes. And what's really cool about microkernel operating systems, especially things like QNX, is because the kernel is so small, you can actually embed it on a chip and have it known as an embedded operating system. So it's actually in hardware. And that's actually really good for real-time operating systems because that will make them even faster to respond to events because it's actually in hardware. So it doesn't actually, you don't actually have to load things from disk and then stuff like that. So that's really cool. And what is in the microkernel? So it has interrupt redirection. You'll note it doesn't say interrupt handling, it says redirection. It has timers, a scheduler, and inter-process communication. But everything else, including the implementation of virtual memory, is a user process. And they're able to achieve this via the message passing, which is one of the forms of inter-process communication. So that's kind of cool. It's kind of neat. Now, who uses QNX? Now, in Canada, there's always these initiatives that, a certain percentage of the software and media that's played on the radio and so on has to be of Canadian origin. So one of the original places where QNX was used was actually the Ontario School Board system. But where you actually see QNX used today is generally for industrial applications and vehicles, and that includes cars. So, and I really hate this word, infotainment. You know how your car has like the little screen in them now? I installed one in my car, but that was mostly so the kids could watch movies. My car definitely didn't come with one by default. But anyways, so those little computers that play music and, have like a map and all that, a lot of them are actually running QNX. So navigation systems, and that includes ones that you see in aircrafts as well. So some of them are actually running QNX. Things like industrial robots, so manufacturing robots, a lot of them will run things like QNX because it's a real-time operating system, so they can actually respond to things very, very quickly. Carrier grade routers. Now, what does that even mean? That means like the routers that like Rogers would use or Bell would use or AT&T would use, like the big mother routers. Not the ones you have in your house, although I'm probably getting to the point where I need one. When even your light bulbs are connected to your Wi-Fi, you start to have problems. And then, of course, BlackBerry at one point had this tablet called the Playbook, and I don't even know if they make it anymore, but that ran QNX, and their phones run QNX. And actually, another big company that uses QNX is actually Ford, although Ford has got a lot of Microsoft connections these days, too. I'm not sure I want Windows in my car, though, to be honest. All right, so that's QNX. Nice Waterloo connection there. So, then, what are we going to talk about today? Oh, it's one of my favorite topics. I know I say that all the time, but I'm allowed to be a little weird like that. So we are going to move on to the following module, devices and I/O. And again, this is posted to the course website, so you can grab it from there. So, we've talked about a lot of the internal implementation details of operating systems. We've talked about how threading works. We've talked about processes. We've talked about system calls. We've talked about how virtual memory works, so we know how abstractions work. And we've talked about how scheduling works, so we know how to choose another thread when there's a context switch. But something that we've completely avoided talking about is how does the operating system actually interact with physical hardware? How do you actually interact with the keyboard? How do you implement time-shared preemption? Because that actually needs to have the operating system interact with the clock, which is actually a device on your computer. So how do we actually communicate with these different physical devices on the computer? And how do we tell them what to do and receive responses from them? Now, this topic is a little bit near and dear to me because I actually used to write device drivers for printers for Linux. So I have written my fair share of code in this area. So I've written device drivers for what are known as POS devices. Now, funny story about that was, the first time I was working, it was actually at Epson, and I sit down at my desk, and I think this is actually the second time I did a co-op there. I did like 4 or something. And I sit down at my desk, and my boss comes by, and he drops a pile of circuit boards on my desk, and I'm like, okay, great. What is this? It was a printer. I had to assemble myself, so I assembled it myself. That's kind of fun. But it was this POS device, and I didn't know what that meant, and I didn't realize that was a formal term for a group of devices. I thought they were calling it a POS device because they dumped a pile of circuit boards on my desk, and the case to the printer was this wooden frame that they had, mashed together with some glue. So I thought when they said POS device, I thought they were saying this is a piece of shit device. Not realizing that POS device actually is a real thing, and it doesn't mean that. It means point of sale. So what a point of sale device is it's the receipt printers in restaurants and like cash registers. They're point of sale devices, and they need drivers. So I've done a lot of driver development for those devices, but I've also done driver development for dot matrix printers. And I know you're probably thinking, like, what's a dot matrix printer? Why are we still talking about this in 2021? Well, what's interesting is, so dot matrix, for those of you who aren't aware, is known as an impact printer. And what it is it has a ribbon of ink. It's like a fabric ribbon, and it has ink on it. And there's a little hammer that hammers through the ribbon and smashes into the paper to put the ink onto the paper. And they're really, really loud, like really loud. So why are people using these devices? Why was I writing device drivers for these in the 2000s? Well, because this kind of printer, this impact printer, is the only thing capable of printing carbon copy forms. Because of course, carbon copy forms need pressure to make sure that whatever you print on the top actually goes through to the bottom. And a laser printer doesn't give you pressure, and an inkjet doesn't give you pressure. Only the impact printer gives you pressure. So if I seem overly excited about device drivers, it's because this is where I actually have a lot of experience. So when we're talking about devices, what all kinds of devices are we talking about? Obviously, printers are a type of device. They are something that plugs into your computer. A printer is an output device. We don't use the printer to input information. Now, of course, if we had some combination like I have down in my basement, I have a combination scanner, copier, printer thingy. So a scanner, that functionality would be an input device, but a printer is an output device. Your keyboard is an input device. It's not an output device because the keyboard isn't going to start typing on its own to send secret messages to me. That doesn't work like that. Things like a touch screen. So I have, and I know you can't see it, I actually have another computer on my desk here, and it's a tablet, and it has a screen that has touch interaction. That is an input and an output device. Now, those are kind of obvious devices because we know things like a mouse is an input device, a keyboard is an input device, a screen is an output device. But there's also a lot of devices that we don't think about. For example, disk drives are devices. So whether you have an SSD in your laptop or your desktop, or whether you have an actual mechanical drive with spinning parts, that is a device. Things like your network card, your network interface, that is also a device. And it is actually an input-output device because, of course, packets are going to go out over your network device and they're going to arrive over your device. And then you can have things like character-oriented graphics, things like a text screen, a serial console where we take character input and output. And then one of the most interesting devices in your computer, which nobody thinks about as being a device, is the clock. And every computer has a clock. And what's really interesting is if you actually look at a lot of motherboards, they actually have watch batteries on them. And the watch battery is actually a battery for the clock so that the clock keeps on ticking. And the first computer that I had didn't have a watch battery for its clock. It actually had like a pack of, I think it was 6 AA batteries for its clock. And it was like this whole battery pack inside the computer for the clock. And it's because we need to keep track of what time it is, even when the computer is off. Now, mine clock batteries were dead, and it didn't matter because my computer didn't have a hard drive, and I didn't care what date it was. As long as there was power, the clock would tick, and then everything would work. It was fine. In today's computers, though, we need that clock to keep going. But it is actually a device. It's on your motherboard. It's not like something that plugs into the motherboard. It's actually on your motherboard. And there's all kinds of other devices that you can have. I mean, you can have USB-attached flowers that kind of dance and sing and do silly things like that. A CD drive, if you still have it, a floppy drive, if you have one of those. Your graphics card is a device. Sound cards, all of those different things are all devices. And when we're talking about devices, there's some terminology that's really important to know. And I know we don't talk about a lot of things with respect to devices in CS, but we'll talk a little bit about it here. So, question on Twitch first. Is a clock an input or an output device? So what's interesting about the clock is I want to say it's mostly an output device. So you could tell the clock to do something, but you can't change what time it is. So mostly the clock is an output device. I mean, you can on some computer clocks, you can set them in like the BIOS, but that's not a usual feature. We usually consider the clock, I want to say, like an output device. All right, so one of the big terms around hardware is this concept of a bus. And I don't mean like the yellow school buses or like one of the Grand River buses. What I'm talking about is a bus is, you could consider it a wire that all these devices are actually plugged into. So I'm actually going to open up OneNote here because I actually want to draw this for you because I think it's kind of interesting. And maybe you did this in CS350. I don't remember. For me, CS350 was almost 20 years ago, so I really don't remember what happened in that course. Let's go to a new page. And let's attach the drawing tablet here. Okay, it's connected. So what you've got with a bus is you can think of it as this path like this. It's this wire. So this is our bus. And I want to call this the main bus. And what you've got coming off of it is things like CPUs attached to the bus. And then your disk is attached to the bus. And RAM is attached to the bus. And let's say your network. All of these things are attached to the bus. And what happens is you can send electrical signals down this bus and every device will actually receive it. So if the CPU sends out a message down the bus, the disk receives it, RAM receives it, and the network and everything attached to the bus is going to receive it. So it's not kind of like a directed, the CPU can only talk to RAM on the bus. Anything that is on the bus will receive every message that goes on the bus. And we will talk about that a little bit later as to how do you figure out whether a message is for you or not. So you've got the main bus, and then you've got, and that kind of goes between the CPU and RAM. And then you've also got a peripheral bus. I can't spell. Oh, well. So you've got like a peripheral bus, and this is where things like your keyboard are attached and all of the things like that. And then there's what's known as a bridge. And a bridge, oh goodness, that's really good spelling. A bridge is going to connect two buses together. So if we need to have something on the peripheral bus send a message to something that's on the main bus, they can actually do that. And of course, something like a keyboard, when we push a key, it needs to raise an interrupt, which means the electrical signal from the key being pushed needs to travel from the peripheral bus over the bridge to the main bus to send it to the CPU. So there's things in a really, really rough nutshell. All right. So the main bus or terminal bus, that is going to be the bus that actually goes between the CPU and RAM, and there's other things that are actually connected to it. And the peripheral bus is actually where most of the devices actually live. And then the bridge can connect to them, and you can have communication between them. But this is your big one. And this is going to be the fastest one, too. So if I wanted to communicate with a device, I need to tell that device something to do. Let's suppose this is a printer, and I want to tell the printer to print a job. How am I going to pass instructions to that printer to tell it what to do? Well, you can communicate with a device through its device registers. So every device actually has a bit of computation power on its own, and it's not usually much. So something like a keyboard doesn't really have much computation power, but it's got just a little bit. The same with something like this little tablet here, although this tablet admittedly probably has a lot more going on in it than a keyboard does, because it's going to be sensitive to pressures and positions, and then there's all kinds of other settings for it. So on the little bit of computational hardware that these devices have, they will have what's known as device registers. And they're kind of like registers on your CPU, except they have very specific purposes. So there's not like, some might have general purpose registers for storing intermediate values, but most devices have just these very specific purpose registers. And there are three primary types of registers. So there's the status register, and that register is typically going to be read. And if you read from a device register that is of the type status, it is going to tell you something about the device. So for example, if let's talk about the clock device for a second. If I read from the time register, the current time register, the current time is a status register, it is going to tell me what time it is right now. So it's telling you something about the device's state. Now, sometimes it might say something like, I am done what you asked me to do. I had an error while doing what you asked me to do. There are all different kinds of messages that might be in a status register. Then there's a command register. And this register you typically write. And when you write to a command register, you are telling the device to do something. So if I want to print a character onto the screen, I might write a character to a command register, and the act of writing to the command register is going to tell the device, okay, whatever the person just wrote in this register, I need to write it onto the screen. So command, we write to it to tell the device to do something. And then we have the data register, which can be read or written, and it's for transferring larger blocks of data to and from the device. For example, if we were trying to communicate with our disk drive, we are not going to do it one byte at a time. We actually want to transfer larger blocks of data between our RAM and our disk. So we have a data transfer buffer, and we will transfer an entire buffer of data. Or we might have a transfer buffer for a keyboard because we might be typing very fast, but the operating system may not be that fast at clearing the characters out of the buffer. I don't know if you've ever had like a character log where you type so fast that the computer can't keep up, and it actually takes a minute for the characters to show up. Well, it's because the keyboard keeps a buffer of the characters that are typed, and then we grab them one at a time. That doesn't really happen on modern computers, but on the computers I had in the 90s, that did happen on occasion. Also, when cats run across the keyboard, that can cause problems too. Or a goose, maybe. I didn't have any geese in my house, just lots of cats. All right. Now, what's really interesting is that sometimes we actually combine registers. So because a status register would be read to tell us something about the device, why don't we combine a status and a command register together? So if I read from a status and command register, it tells me what the device is doing. And if I write to the status and command register, I'm telling the device to do something. And so you will often see combinations, status and command, data and command, and things like that. So what I want to do now is I want to actually show you the specifications for some devices in OS 161. So Sys 161, our simulated MIPS R3000. And if you were an operating system developer, you would be getting these spec sheets from the hardware manufacturers so that you could actually make the device drivers for your operating system. And these might be really small spec sheets, or they might be really, really big. So I was working at Google like 13 years ago or something, and I was actually working in the hardware group, and we were working with NVIDIA's spec sheet, and it wasn't a sheet. The NVIDIA spec sheet was like this book this thick. So be thankful we're not going to go over something like that here. We're just going to go over little simple devices. But the hardware manufacturers provide these specs to the operating system manufacturers so that they can actually create the correct device drivers. So we'll look at the clock one. The clock one is the most important one because without the clock device, we can't do preemptive concurrency. Remember, in order to do preemption, we need to have the clock periodically fire an interrupt. So in order to get that behavior, we need to be able to communicate with the clock. So let's actually talk about the clock. So this is our specs. We are going to ignore the first two columns of this table for now, and I will revisit what these are in a little bit. For now, we're just going to look at the last two columns. So first off, we have two status registers for the current time, and the current time is provided as the current time in seconds and the current time in nanoseconds. Now you might be thinking to yourself, oh, so it's going to say like it's 9:58 a.m. on March, I guess, 11th. Actually, that's not how we represent time in the clock. What the time is the number of seconds or nanoseconds that have elapsed since what's known as the epoch. And the epoch is January 1st, 1970, midnight. So that's the epoch. So the current time is how many seconds have elapsed since midnight on January 1st, 1970. That's time 0. Now, what's really interesting about this is these registers are 4 bytes, which means at some point we will actually overflow this register, and we actually know when this is going to happen. It's going to happen in your lifetime, and it's going to happen in my lifetime. It's going to happen on January 19th, 2038 at 3:14:07 GMT. That is when we will overflow the current time register on clocks. They call it the end of Unix time. And apparently there's parties scheduled and things like that because, you know, it's more exciting than Y2K, right? So this is actually an interesting thing. So how do we solve this problem? Do we start making devices with like 8-byte registers for the time? I mean, we could do that. Or we could set a new epoch and just reset the clock and let people worry about it later. There's lots of different ways that we can handle this, but it will have to be handled because there will be an end of Unix time. All right, so we've got 2 registers for the current time. Then we've got these 2 status and command registers here. One is interrupt and one is called countdown time. So countdown time. If you write a number to countdown time, and it's specified in the units of microseconds, it is going to initiate a countdown for that many microseconds. So if I write a countdown for 400 microseconds, then writing 400 to that register is going to initiate a countdown for 400 microseconds. When it expires, this interrupt register is, so first off, when the countdown expires, the device fires an interrupt, which means it fires an electrical signal to the CPU to say, I've done something, you should help me out. And then what's going to happen is when the operating system picks up that, it can look at this register and say, oh yes, you fired an interrupt. It's going to have a 0 in here. or some value to indicate the countdown has expired. And so we're going to clear this register to tell the clock, yes, we've handled it. You can stop refiring that interrupt. And then we can move on from there. So when we clear this register, so there's going to be something in here to indicate the countdown has expired. And when we clear it, we're telling the clock, okay, we are aware that this has been handled. It kind of creates this contract in a way. So we put a mark in here to indicate something has happened, and we clear it in the operating system to let the device know, okay, we know you're good to go now. Okay. So what's this restart on expiry? Now, every time the clock countdown expires, I don't want to have to reset it. It would be really nice if my clock could restart the countdown on its own. So if we write a value to restart on expiry, then what's going to happen, and then we write a number to countdown time, then when the countdown expires, the interrupt will still fire, but the countdown will start all over on its own again. So for example, if you wanted to have preemptive concurrency, where you had the clock throw an interrupt every 100 microseconds, then you would write a 1 to restart on expiry, and then you'd write 100 to countdown time, and that would actually set that interrupt off every 100 microseconds. You get it. Down, 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 down. So the question we have on Twitch now is, does the countdown time do the counting down, or is that somewhere else? So, I'm not sure if there are any other internal registers where it actually keeps track of the countdown time for the restart on expiry. I'm assuming there is. And I don't have all of the details for the implementation of this particular register, but a lot of times what happens when you read the countdown time, it will tell you how many microseconds are left in the countdown. In some devices. I'm not 100% certain because we don't have the specs for that for this simulated one. Now, there's one final register we have, and that is this command register for the speaker. And people are like, what does the speaker have to do with the clock? But that's actually one of the really weird things about clock devices, is they actually have a speaker attached to them. And in the old days, if you opened up like an old computer in like the 80s or 90s, there would actually be like a physical little crappy speaker on a wire attached to your motherboard. And it was actually attached to the clock. And what happens is if you write to the speaker register, a beep goes out of that speaker. So like on old desktops, there would always be like a wire going to a speaker at the very front of the computer, the desktop case. And the case would have like the speaker built in because it didn't always come with the motherboard. And you'd plug that in and it'd be plugged in and attached to the clock. And then when you boot the computer, it would beep. And so why does the clock actually have this speaker attached to it? To set off alarms, I want to say. So what's interesting is different architectures have actually used this in different ways. So for example, in the 80s and 90s, that speaker was actually used on boot to indicate there was a problem booting the actual hardware. So for example, if you got like 2 long beeps followed by a short beep, that might indicate that there was like a failure with one of the peripherals or something. And actually what's interesting is Apple products actually still do this. Now, they don't have, as far as I know, a separate speaker. I think they're just using the regular speakers on the system, the regular audio channels. But the idea is that if you have a problem booting like your MacBook, because there's some kind of hardware problem, it will play an audible tone. Now, you can disable it, which I do because it's annoying. But it will play an audible tone. Whereas other devices have decided that the audible tone isn't really a good idea because you might not hear it correctly. So some of them have an LED or a combination of LEDs that will flash to indicate or have certain patterns to indicate there's a problem with the hardware booting. My research lab desktop downstairs, which has currently got a problem with it, actually has an LCD panel that actually displays the error code, which I'm getting error code 68 right now. So I've got to get that fixed. Error code 68 means there's a problem with the peripheral bus. Yeah, fun stuff. All right, so you can use the speaker to represent and set off an alarm. you can use the speaker to represent, to create audible error codes. And another place where this actually fires is if you're at the terminal and you backspace too many times, you notice it beeps. It's actually usually going through the clock, actually. Or at least it used to go through the clock, so that's kind of an interesting thing. And if you want to really annoy your coworkers because you've got an open office plan, you know, you could write a device driver that plays songs on it. All kinds of fun things you can do with that. So we could actually create now create some code to actually implement preemptive concurrency. So that's kind of fun. Let's look at another device then. So that's our clock device. Let's look at the serial console device. And this is used for input and output of characters. It's kind of an old-fashioned device. And it only has 3 device registers. So it has a character buffer. And this is a command and data register, which is interesting. So what happens if you write to the character buffer, you are saying, okay, I want you to output these characters to the serial console. And if you read from the character buffer, then you are getting data from the serial console, which may come from the keyboard or whatever. And then we have 2 status registers, write IRQ and read IRQ. Remember that IRQ actually means interrupt, and I don't know why that's the short form for interrupt, but it is, and it just always has been. But the idea is that if you are since interaction with the serial console is a time-consuming process, like it's not an instant thing, it's not as quick to interact with as the clock. You can kind of think of the serial console as like almost like a terminal where it's accepting characters and displaying characters. So the idea is that that's going to be a little slower. So the act of writing to the serial console is going to take time. And if you are writing characters to the serial console and you issue another write command, what's really interesting is that behavior is undefined. The manufacturer has actually said, if you try to write while a write is in progress, we don't know what's going to happen. So you might get a mangled character, they might output in the wrong order, the device may actually fault, catch on fire. And a lot of hardware, by the way, has things like undefined. If you don't do things properly, we don't know what's going to happen, so we say it's undefined. So these registers here, write IRQ and read IRQ, are used to indicate if a write is in progress or a read is in progress. And then the idea is the software that's going to interact with these device registers is going to need to, before you start your operation with the serial console, you need to check, is there a write in progress? Because if there is, I need to wait for it to stop. And once it's done, there will be a code in here that indicates the write has completed, you can proceed. And there will also, we can use the write IRQ and read IRQ registers to pass any error codes back and forth. So that's kind of cool. Now, by the way, once the serial console has completed reading or writing characters, it again fires an interrupt. So it sends an electrical signal, and at which point the kernel is going to need to clear these and deal with any error codes to let the device know, okay, you are clear to do something else now. All right. So we're going to have a spec sheet like this for every single device in your computer. And as I said before, that spec sheet might actually be, just 3 lines, or it could actually be a great big thick tome like this for like the NVIDIA graphics cards. But that only tells you what registers there exist, and it tells you where you can find them and how big they are, and it tells you how to use those registers to issue commands and learn about error codes on the device. But what they don't tell you is, how do I actually write the device driver to interact with the device? So let's talk about device drivers now. So first off, a device driver is a bit of code that is written to interact with a piece of hardware. And I know at the very top of this page, it says a device driver is part of the kernel that interacts with the device. And I want to clarify that. Not all device drivers are part of the kernel. Most of them are. And what's really interesting is device drivers are actually loadable kernel parts. If you think about it this way, let's suppose you went to the store and you bought one of these lovely tablet devices. I know. Not many people have these days, but there you go. Let's suppose you bought one. You plug it into your computer. Before you plugged it into your computer didn't have the device driver for it. After you plug it into your computer, your operating system is either going to notice that there's a piece of unidentified hardware attached, and it's going to find the driver and load it for you, or you're going to have to manually install it. And something like this is going to have a kernel device driver, and it is going to become a loadable part of your kernel. Now, how does that work? Well, in Windows, there used to be this folder called Win32, and I don't know what it's called anymore because I don't use Windows that much. But if you put a DLL, so a dynamically linked library, that was your device driver, in that folder, the DLLs in that folder were loadable kernel modules. And in the Linux kernel, you can actually do that too, except you use the system called mod probe. So if you use the mod probe command, you can find out which device drivers, which kernel modules are currently loaded. You can restart them. You can load new ones. You can unload them. So there are parts of your kernel that can be loaded on demand. So that's kind of cool. And most device drivers are loadable kernel modules and behave like that, but not all drivers are in the kernel. So, in Linux, new Linux, a lot of printer drivers live in userland. That's really weird. So, a lot of printer drivers, so in particular, a lot of printer drivers are actually a part of something called GhostScript, and which is part of the CUPS printing system that runs. And I don't want to talk about that because it's not very fun to talk about. But what's interesting, so printers actually have their own assembly language. And what happens when you hit print on a document is GhostScript, or whatever tool is being run, is going to take your document and convert it to the assembly language that the printer speaks. That doesn't need to be a part of the kernel because you haven't actually communicated with the device at all. All you have done is essentially assembled something. It's just like a compiler. It's just an assembler. And then what happens is once you have translated the print document into the assembly language for the printer, you are going to send it to whatever port the printer is plugged on. Now, a lot of the printers that I was working with were attached to the serial port, which needs no special driver whatsoever. USB did actually need a special kernel printer driver for that, but for things that were attached to the serial port, and I know your laptop doesn't have a serial port anymore, but the serial port on a desktop used to be the file dev tty0. So you take the assembly file that you created for the printer and you write it to dev tty0, and that would send it to the printer device. Now, there will be a driver that handles writing to, the kernel is involved with writing to dev tty0 because that is, a port. It is attached, it's part of the peripheral bus. But there's no specific kernel driver for the printer. It's just a user program. So that's kind of interesting. Some device drivers are actually just at the user level, and they don't interact directly with the printer or the device itself. They just send, an assembly file over. So that's kind of... We are going to focus on those device drivers which are a part of the kernel, because that's the majority of them, and it's more interesting. Let's be honest. So let's suppose then we wanted to write to the serial console, and I wanted to write the driver for that. Now remember I said only one write can happen at a time, so we need to use some synchronization in the kernel. Now you're like, oh right, only one thread can write at a time to the serial console. I need a lock. This is actually where we're not going to use the lock. It's faster here to use a semaphore, actually. And that's what we're going to do in device drivers, is we're going to use binary semaphores instead of locks. This will become more apparent as to why we do this as we go on. So we have a binary semaphore for writing to the serial console. So before I trigger a new write, I p the binary semaphore to make sure that I have mutual exclusion on it. And I will either have to wait for the previous operation to complete, or I will be able to proceed because nothing is currently happening. Then I will write the character to the data device register on the serial console. And then I'm going to repeat and poll the device to see when the write has completed. So I'm going to repeatedly read the write IRQ register on the device to see, has this write completed? And until it completes, I'm going to keep polling and polling and polling. And once it completes, I acknowledge completion back to the device by clearing the write IRQ register. And then I let go of my semaphore. I mean, technically I could have used a lock here, but locks don't work in general for devices. We'll talk about that later. The problem with this is polling the device. We're repeatedly checking the device status to see when it's done. This is not very efficient. When the serial console has finished something, it fires an interrupt. So why am I polling the device to see if it's done when the device is going to tell me it's done when it's done? So we could actually write this driver much better. We could create two parts. The first part is instantiating the write. That's the device driver write handler. And then we have the interrupt handler for the serial device. So two parts. The first part, when we want to write to the serial console, we p the semaphore for that device, and then we write the character to the device data register. And then we do nothing. So we may return to the user program, and they may continue execution. Or there may be a context switcher and another thread might run. When the serial console is done its write, it will fire an interrupt, at which point the kernel will respond, and the interrupt handler for the serial device will run, and we will acknowledge, okay, device, I see you have completed this, and then we V the semaphore. Now, this is actually why we need to use semaphores with devices like this, is because the thread that executes this may not be the thread that handles the interrupt. And as you know, a lock can only be released by its owner. Now, it's not that you couldn't do it. It's just that if we wanted to use the lock, we'd have to do a context switch back to the owning thread, and it's just extra work, and we don't want to do that. So using a semaphore here lets us get away with this. So you may be thinking now, every device does this. No device does this. Polling. Actually, so USB does polling. So one of the interesting things about hardware is there's always more than one way to do it. And even if one way seems to be the clear winner, this is the way you should do it, there's always some device that still does it the other way. And what's interesting is in your hardware, there are some devices that use polling, and there are some devices that use this interrupts to let them know that the task is done. USB devices use polling. So my understanding of this was actually that if they wanted USB devices, the USB controller, to be able to fire an interrupt, the electrical signal from the interrupt would either corrupt the data that was being sent over the USB bus, which is bad, or they could add an extra line just for the interrupt, but they didn't want to add an extra line just for an interrupt. So they decided that they would do polling. Now, there's usually a USB controller that actually operates in your hardware, and that might actually do the polling for you and then pass interrupts to the CPU. So there's all kinds of weirdness, but polling still happens with USB. It's kind of interesting. All right. So you get the idea of how to write these drivers, but let's be honest. How do you write to a device driver? Like, is there a book that says, does the CPU know the name of every single device's every single register? Obviously not. So how are we actually going to be writing to these device registers? That doesn't make any sense. Yeah. So there's lots of ways that we do this. So to actually access the device drivers, there are 3 or 4 different ways that we can do this. For simple things like status and command registers and very small transfer buffers, we have something called port mapped I/O and memory mapped I/O. So let's talk about these two. So first off, port mapped I/O. This is an interesting one. You can essentially consider the fact that we have special I/O instructions. So there are special assembly instructions are going to be used with port mapped I/O. What happens is the CPU has a separate address space, and it's much smaller. So like your regular RAM has like 64-bit addressing, and the port mapped address space will use like 8 or 16-bit addressing. So it's a very, very small region of memory. It's special memory. And instead of calling it addresses in the special address space, we call port numbers to differentiate from this is not a part of RAM, this is something else. And what you do is when a device boots, each device register is going to get mapped to one of the ports, or maybe 2 ports or something like that, depending on how big it is. And then what happens is in the device register, or the device driver, when you want to write to a particular device register, you use special in and out instructions, which are the x86 architecture's instructions, to write to specific port numbers. And what happens is, so when you issue these commands to go in and out to port numbers, the device is on the same bus as this memory. And what happens is the device hears every port number, and whether it's an in or an out, over that bus, the same as the actual ports. And so, because it's on a bus, everything on the bus gets every signal. The device knows which port numbers belong to itself. So when it sees, I'm putting something in port number 300, the device says, oh, port 300 is me. So I see somebody is trying to write to port 300, which means that's my restart on expiry register. And so the device will grab that from port 300 because it will know something is that's for it. Okay? And then if it's out port 500, then it will know it needs to write something to port 500. So that these ports are on the same bus as the device, and the device hears all of these addresses, and it has to know which are for itself and which are not for itself because it gets every request. And when it sees one for itself, it can do the appropriate read or write to the actual device registers. So that's port mapped I/O. The downside of port mapped I/O is that this memory, these ports, can't be used in a general way. So if you need to do some kind of arithmetic manipulation of something in a port, you've got to pull it out of the port, do the manipulation in regular memory, and then push it back to the port. So it's very restricted with how you interact with the data in the ports. The advantage, of course, is that this is actually really fast. And it's really fast because the devices are only going to see the port numbers for devices. And it actually has to decode each of these things, which can take time, but it's not going to have as many decodes. So it's actually faster. Much, much faster. But it's very restricted, and there's not a lot of port numbers because it's a small address space. Okay. By the way, your computer does have some port map devices. This is not your computer does all of one and none of the other. Your computer does all of these things. Some devices use port mapped I/O, some of them use other tech. The other tech that's really popular for simple things is called memory mapped I/O. And the idea behind memory mapped I/O is we're not going to have a separate address space for the device registers. We're going to just use a region of memory. What region of addresses should I use? Oh, I'll use KSEG1. So remember how I said there's a small region of KSEG1 addresses are used for talking to devices? This is memory mapped I/O. I'll show you in greater detail soon. So what we're going to do is each of the device registers for our devices are going to map to just a plain old region in RAM. And so a regular address. And so the devices are going to have to be attached to the main bus so that they can hear all of the requests going to RAM. And they're going to need to translate every one to figure out, is this for me? Is this for me? Is this for me? And when they find one that's for it, they will grab the data or do whatever they need to do with it. So the advantages to this one are RAM is a lot bigger, so there's less restrictions on how many device registers we can map. Another advantage is we don't need any special instructions to deal with this because it's just RAM, so it's just loads and stores. And we can just, do regular stuff with it. It's just regular memory. The disadvantage is this is actually slower, and it's slower because the address bus, the main bus with RAM, is actually a very, very busy bus, and only a small proportion of those requests that are going over those bus will actually be for the devices themselves, which means that the device is doing a lot of extra work decoding these addresses that are rarely for them. Whereas with port mapped, they're decoding less, and the probability of one of those things being for you is much higher. So it's just the devices are doing a lot more decoding when you do memory mapped I/O. OS 161, by the way, does memory mapped I/O. Your computer uses both. So now let's talk about KSEG1 in greater detail. So for the memory mapped I/O of OS 161, we have a predetermined region of KSEG1 addresses that we're going to use. And they actually map to the very end of the 512 megabytes in physical memory. So what happens is we've set aside 32 slots for devices. And each of those slots is 64 kilobytes. I'm not sure if that's bytes or kilobytes. I should go back and check this back again. Anyways, we have 32 of these slots. Each device maps itself to one of these slots on boot. And then how do I know where in a slot that each device register is? Well, that's what this data is for. This offset here is your position within the slot where that device register is, and the size is how big it is. So this information here tells us where within our memory mapped slot we can find each of those device registers. So that's kind of cool, right? And this, again, is only using the very tail end of KSEG1 addresses, which the OS 161 and KSEG 0 will not use because we have set this aside. And now we know the difference between I'm talking to a device and I'm not talking to a device. So it's kind of neat, right? But what if I want to transfer a lot of data? Like, that's really good for like 1 or 2 integers at a time. But what if I actually want to like transfer a 20 terabyte file from my one RAID array to my other RAID array? Because, I have a backup for my RAID array. So what would I do then? How would I do that? How would I transfer a large block of data? Because there's 2 ways that you could really do this. I mean, the way that we would most of us think of would be program controlled I/O, which is the CPU is actively going to take data from RAM and transfer it to the device. Like, it's okay, here's 4 bytes, here you go device, here you go, here's the next 4 bytes. The problem with program controlled I/O is that the CPU is actually performing the transfer. The CPU is actively involved with reading from some location in RAM, writing to some other location in RAM so the device register can read it. If I'm transferring 20 terabytes, my CPU is going to be tied up for 2 days straight, which means my computer's totally unusable. Program controlled I/O. This is actually what OS 161 does, by the way, and that's fine because it's a toy, right? And some devices on your computer still use program controlled I/O. But what's more common these days is this thing called direct memory access, or DMA. And you might have heard of something called a DMA controller. We're not going to go into that level of detail. We're going to do a really high level. This isn't engineering. You're welcome to read more about it, of course. So the idea behind direct memory access is instead there's this thing called the DMA controller. And we're essentially going to say, okay, we want to tell the disk to get the data your damn self. So the CPU is going to initiate contact with the disk, and this happens actually via the DMA controller. And it says, okay, you need to transfer some data. Here is the start address, and here is the length, and here's where you need to put it on yourself. Okay, see you later. And then the disk, since it is attached to the memory bus, the main bus, moseys on over to memory and grabs the data itself. It knows where to start, it knows how many bytes to transfer, and where to put it. And again, the DMA controller is going to facilitate a lot of this, but the CPU is not involved. The disk does the transfer on its own because the DMA controller via the CPU has told it how to do it. Once the transfer is completed to the disk and the DMA controller will fire an interrupt back to the CPU to say the transfer is done. And that's it. What's nice about DMA is that the CPU is not busy doing the data transfer. The disk does it itself, which means the CPU can do other things, like decompress video so you can watch YouTube or whatever. So, for large memory transfers, DMA is the way to go. And your disks do this all the time. It didn't work so well, so I think some of the older computers I had did not have a DMA controller, and so they did program controlled I/O. And I want to say it wasn't a big deal really in the late 80s, early 90s, because again, we weren't really dealing with a lot big data. My very first computer, true story, did not have a hard drive. There was no hard drive in it at all. It still worked. You're probably wondering, how did I do anything? I had 2 floppy drives, and in floppy drive A, you put your program disk, and then you turn your computer on because everything was self-booting. And then you put your data disk, so if you wanted to like run WordPerfect would be in disk drive A, and then in disk drive B, you'd put the disk where you actually store your files. It wasn't bad. But my first 486 only had, I think, 600 megabytes for a hard drive, and that was actually considered quite big. Files weren't that big back then. All right. So your computer doesn't just do this, port mapped and memory mapped I/O. It also does program controlled I/O and direct memory access. So there are lots of different ways that we can actually transfer data from RAM into the actual device and back. And it really depends on the device and your architecture. And that's why we don't go into too great of detail. It's because implementations of program controlled I/O and DMA are very specific. All right. So, I want to briefly introduce our next topic here. I want to look at, we've talked about the clock, which is a very, very important device in your computer, but there's one other super important device in your computer, and that's your hard drive. And I know my first computer didn't have a hard drive, but all pretty much computers since then did. I mean, so I had a 1981 IBM PC, and it didn't have hard drive. You could buy a 5 meg hard drive, and it was about this big and about that thick. It weighed about 25 pounds. It was heavy. It was huge. My friend had one in her XT. She gave it to me later, but it didn't fit in my computer because I had multiple drives. Hard drives are really important to us because we don't have multiple disk drives. We want the data to be there for us always, and we don't have to flip through containers of disks trying to find the disk we actually want. But what we're really talking about is persistent storage. We have devices in our computer that store data even when the power goes off. And it's important to distinguish when the power goes off because your RAM, when it loses power, actually loses the values that are stored within it. The only way that RAM can store values is if it has continuous source of power. Whereas your disk drive, like maybe you have one in your laptop or maybe you have a desktop with a whole bunch of things, if there's no power, the data is still there. Like I've got some external ones up here. I haven't plugged them in like a year, but they keep their data. And this is important for things like loading operating systems and programs and so on and so forth, because again, we don't want to have to go fishing around for the disk for that particular program. Sometimes instead of persistent, of course, we call this non-volatile storage as well. And what's interesting is this is not a new concept. So you might think, oh, well, persistent storage, it's only been around since like the 80s. No. Well, maybe it's only been around since the 50s. Actually, the concept of storing data or a program persistently goes back to the 1700s. I know there's no computers in the 1700s, but there kind of was. So in the 1700s, there was this thing called the Jacquard weaving loom. And the idea is they were trying to weave patterns into fabric. And if a human is controlling the pattern of the loom, I've never woven anything in my life, But if a human was trying to do that, they're very prone to making mistakes. So they wanted to try to make a loom that could automatically shift things so that all the human had to do was move the little shuttle thing back and forth. And then making sure the correct threads were forward and backwards was handled by this program, a mechanical program, effectively. And they stored the mechanical program on punched metal cards that were strung together in a long string. And the idea was there were these gears with teeth, and the teeth would go through different holes in the metal cards and cause the loom to move in specific ways. But in a way, those punched metal cards were the first way that we persistently stored a program. And that's in the 1700s. And the concept of punched metal or punched paper actually persisted right through the 1970s. So they had punched cards where programs were stored, and you're actually going to see those in our video today. But smaller computers even used punched paper tapes, which were a really bad idea. So like the PDP-1 from DEC actually had a punched paper tape, and it's this thin little paper tape about 1 inch wide that you punch holes in, and it's like really thin. And the problem is that it rips so easily. I've actually seen like people have been like copying, like making copies of paper tapes, and like the paper tape copy machine, which like reads the holes and then prints the holes on the next page, will like rip the tape. So it's not very good. But anyways, this idea actually persisted for hundreds of years. And then in the early 1930s, people had this idea of actually using magnetic drums. And I mean like giant things to store data persistently, and magnetic tapes, which was the 1920s. And again, what's going on here is you've got a surface that's covered in like a ferromagnetic material, or you're using magnets in some way to, and it's the direction of the magnetic field is storing as either a 1 or a 0. And one of the cool things about that is, so there's this thing called like solid state memory is kind of very similar to these magnetic drums. One of them is this core memory boards, which are really, really cool. It's like these knitted copper wires, and then at the junctions, they've got little magnets. It's really cool. I want a piece of it. Like I want a piece of the Univex memory, but it's really expensive, so I can't afford it. It's really cool looking though. Now, then the idea of a floppy drive, which is just a smaller piece of magnetic material. They've been around since the 70s, and they persisted through to the 1920s, or to the 2000s. Hard disks, which were like, I could literally stand Vitruvian Man style. They were that big. They were huge things. They've actually been around since the 1950s, although they didn't store as much data as they do today. Now, what are the other interesting things I want to say? Magnetic tapes. Magnetic tapes. They've been around since the 1920s, and I want to tell you, they are still used today. CSCF, in fact, still uses magnetic tapes. Yeah, CSCF is using magnetic tapes. Now, what are they using them for? Archives. Now, why? Because a little tape, and nowadays you can get the tapes, there's just little cartridges like this big, and they store terabytes of data, and they're at a fraction of the cost of a hard drive. So magnetic tapes are actually still used by many companies, and especially in the film industry, to do long-term archival storage. They are very slow, obviously, because if you want to find anything on it, it's like a linear search. But it's really great for archives. So they are still actually used today. Then, of course, throughout the 80s and 90s and early 2000s, we had different optical media. So we had CDs, DVDs, and Blu-rays. And what that is they have like a reflective surface where they've pitted it, and depending on how the laser gets reflected, it's a 1 or a 0. And then solid state memory, so SSDs, that's actually been around since the 70s, but it only really became popular and feasible for everybody in about the 90s. And now we have this thing called ReRAM, or Resistive Ram, and what that is it's RAM that actually keeps its power. So it can keep data. Even in the absence of power. So that's really cool. So there's all kinds of different persistent storage out there. And what we're going to focus on in episode number 18, is we're actually going to talk about how does a hard drive, i.e. a mechanical hard drive, you know, the big 8 terabyte things or 12 terabyte things you can get these days. How does that actually work, and how do we write the device driver for that? And then we're going to talk about how SSDs work after that. So don't worry. I know a lot of people don't use mechanical drives anymore, and people use SSDs. We're going to talk about both of those. So that will be episode number 18. Episode 17, just to remind you, is going to be talking about assignment 3. So we're going to leave it there. And we will see you next Thursday, so a week from today. And on Twitch, I'm half transparent. Yeah, I'm probably looking pretty green today, so I don't know. My the green screen software is probably filtering part of me out. Sorry. I'll adjust it later. All right, so we'll see you Thursday.
Atta girl.
Hey, what the hell are you doing? You can't be in here. Who are you?
I'm with the West Computing Group. Dorothy Vaughn, sir.
Well, this is a very delicate piece of equipment.
I'm sorry, sir. I'm just trying to be helpful.
Bill, we've got numbers.
What kind of numbers?
Floppy. What's your name again?
Dorothy Vaughn.
Dorothy Ram.